All right, section 2.4, the precise definition of a limit. All right, so we've addressed the definition of a limit, or at least the general idea as far as what a limit is, right, what it's measuring. And part of our discussion that we've had with the limits up to this point, we were using language like uh, f of x would be arbitrarily close to L if we picked our x values sufficiently close to A. And that was the language we had previously used. And then the question was, realistic or logically, I guess, is well, how close is close enough, right? And so we said when we were doing those tables of values, how close does x have to be to A? Well, we would pick those x values that kept getting closer and closer to our A value, like 0.9, 0.99, and 0.999, and so on and so forth, until you were able to make an observation to where I could say, all right, I can tell you that the values of f of x are getting close to some number, right? And until we could make that determination, and so you kept picking values that were close enough until you can make the observation about what the limit value was. Okay, so this is more the specific approach to, okay, well, how close do I actually have to be in order to guarantee that my function value is approaching this specific number? That's the question that we're going to address now. We're going to do it two different ways. The first way is going to be kind of specific, in that if I tell you how close I want f of x to be to L, then you should be able to tell me how close x has to be to A as a specific value. Then we're going to also do it more generically, to where we could address any given distance between f of x and L. Right? So, and if that changes, or if I choose different values there, then that of course is going to affect the distance between x and A. So what is the relationship between the two? And so you could give any value for that distance between f of x and L, and then I can automatically tell you what the distance between x and A has to be. So that's the more generic approach to it. And this section, it's a little bit tricky. It's one of the more hair-pulling sections that we deal with, just because, like I said, the generic nature of it. So be careful with this section. Pay your dues like everybody else. And this what we call epsilon delta definition of the limit. It can be a little tricky. So anyway, we'll go through it. I'll give you a few examples of what I'm talking about. So here's our definition for the limit. Now the first part of this is similar to what we've already said, just a little bit different notation and terminology. But basically we said, like, our definition, let's let f be a function defined on some open interval that contains the number A, except possibly at A itself, because remember we keep talking about with limits as x approaches A. I don't care what happens at A. I don't have to be defined at A. A is irrelevant. It's all about what happens as we approach A. All right, so we have our function that is a function defined on an interval that contains that number A. Doesn't have to be defined at A. Then we said that the limit of f of x as x approaches A is L, and we would use that little notation, limit as f of x, or limit of f of x as x approaches A is L. And then here's the new part of this definition. If for some number epsilon greater than 0, that's the Greek letter epsilon, there is a number delta greater than 0. That's the lowercase delta. I think I mentioned the uppercase delta to y'all previously, but there's the lowercase delta. Such that if, and here's the big statement, the distance between x and A is less than delta, then the distance between f of x and L is less than epsilon. Right, and notice the use of absolute value here. Remember, absolute value is used to calculate distance. Right, generically, absolute value of a number is its distance from 0. So here we're using absolute value to represent or give us the distance between x and A on the left, f of x and L on the right. So that way, when we say that the distance between x and A is less than delta, doesn't matter which side of A you're on, right? So if I measure the distance from x to A on the left or the distance from x to A on the right, we want it to be less than some number. That number is always going to be a positive value, delta greater than 0. So in order to ensure that we have a positive value, distance between those 2 points, we put the absolute value on it. Right? So that's the reason for absolute value here. It's used to calculate distance. It also ensures that that value is positive. So we're saying that then, if that distance between x and a is less than delta, then that distance between f of x and L is less than some epsilon value. Right? And so if you tell me then how close you want this to be, right? How close do we need the function to be to L? Then I can tell you how close to A I have to pick those x values in order to accomplish that. All right? So that's the statement. The next piece of this is the algebra. Right? Now, go back to algebra, definition of absolute value. When you have an absolute value less than a positive value, less than a positive constant, that means that whatever is in the absolute value would have to be between the positive and negative of that constant. Right? So you think about like absolute value of 3, for example, is 3. Absolute value of negative 3 is 3. Right? So in other words, that distance from 0, right, could be either 3 to the left or 3 to the right, but it's between negative 3 and 3. And so any number that has an absolute value that's less than 3 would have to be between negative 3 and 3 on our number line. So in this case, the distance between x and a less than delta. That means x minus a, whatever's in the absolute value, has to be between the negative and positive. And that way we can solve this for our x values. And I can then say, okay, my x value that I would choose would be in this interval between a minus delta and a plus delta. And that should make sense because, again, we're picking a delta value, which is the distance between our x values, and our specific a value. So that means if I move a distance of delta to the left or to the right of a, right, a minus delta or a plus delta, then that gives me the interval in which those x values fall. And then it's similar over here on the right for the f of x minus L is less than epsilon. Right? So then the distance between f of x and L, whatever's in the absolute value, would have to be between the positive and negative of our delta value. There, our epsilon value. We get those backwards. Which then means our function values would have to be in the interval from L minus epsilon to L plus epsilon. Right, now again, it's a little weird looking at it in that generic sense. So we'll grind through a couple of examples. I'll show you a little more specifically how this is working and hopefully kind of clarify it a little bit. But here's kind of a graphical representation of what we're talking about. Right, remember our graph as x approaches a, f of x is approaching L. Right, so as we move along our graph, as we approach the a value from the left or from the right, we have our function value approaching our L value. So what we're doing here now, let me clear that up. Is we want to specify now an interval within which, if I choose x values within this interval, which are within a distance of delta on either side of a, right, so a minus delta, a plus delta, then I guarantee you my function values will have to fall in this interval. So that's going to be some distance on either side of L. Now, again, my picture is not perfect. You want pretty pictures, you look in the textbook. Okay? But that's the idea, So once I know what this is, if I know how close to L I want to be, then I should be able to calculate how close to A I need to be with those x values, so that I fall within this part of the graph of our function, which means I'm within that distance of our L value. Okay? So again, it's as vague as I can be. Right? So let's see if we can maybe, in the first couple of examples that we're going to do here, we're going to deal with specific values. So I'm going to say, okay, pick a specific epsilon value. How close to L, how close to the limit do I need my function to be? And then we'll determine exactly what that delta value would then need to be, right? How close to A does x have to be? So we'll call that a graphical approach. to this, and then we'll do the more generic, which is ultimately it's the trickier part. Now I'm going to show you how to do this on the calculator as well. So I do have some calculator pictures for you, because that'll be the easiest way to figure this out. So what we're doing with this first example, we're using a graph to find a number delta. Right, so I want to find that delta value such that f of x is within a distance, there's our epsilon, of L, whenever x is within delta of A. All right. So if I tell you what epsilon is, how close to L do I want f of x to be? We then want to determine what is the delta value, how close to A does my x value, or do my x values have to be to make that happen. Now here's a limit statement, right? And so there's parts to the limit statement that we'll talk about. Now again, we're not finding a limit, we're not evaluating the limit. All we're actually doing is we're proving that this limit statement is actually true, right? That's the idea behind this, right? So I know what this limit is, we can calculate it using our table of values and so forth, and other methods that we're going to talk about. So the idea here is let's prove that that limit statement is true. So that limit as x approaches 1 of x cubed minus 5x plus 6 equals 2, given that limit. How close to 1 does x have to be to ensure that the function is within a distance of 0.2 of its limit? Okay, so we have all these different pieces of, I call it the epsilon delta definition of the limit. So our epsilon delta definition. All right, so I've got the limit as x approaches 1, so that is our a value of our function x cubed minus 5x plus 6 equals L. All right, so there's a, there's f of x, and there is L. Okay? And then we're trying to find how close to 1 does x have to be, that's our delta value, to ensure that the function is within a distance of 0.2 of its limit. There is your epsilon, the distance between f of x and L. All right? So f of x, x cubed minus 5x plus 6, L is 2, A is 1, epsilon is 0.2. We are looking for delta, and that's always your objective with these, is to find delta. So what do we have? We have that the distance between f of x and L is less than epsilon, right? Which means then that distance between f of x and L would have to be between the positive and negative. That's the algebra part of it. Absolute value less than a constant, positive constant. Whatever's in the absolute value falls between the positive and the negative. Which means then our function, and notice I'm just solving this inequality for the function value, the function has to be then between 1.8 and 2.2, and all I do is add 2. Now that should, realistically make sense, because we know what the limit value is. We know the limit is 2 as x approaches 1. And if I want to be within 0.2 of that limit, right, then that means I would be on a distance of 0.2 on either side of that value, which means my function value would have to be between 1.8 and 2.2. So this is kind of the algebraic process. And so when we get to the generic definition, the generic form of this, it'll maybe make a little more sense as far as what we're doing there. Okay, but we can do without this at this point, because we know what the specific values are. But that's the algebra. That's how that works. So calculator. I'm just going to do this on the calculator. So basically, what I'm interested in then is, look, let's graph our function. Right. Graph our function. And then let's look at the function value. Ooh, wrong one. Look at our function values of 1.8 and 2.2. And then let's determine what the x values are that give us those specific y values, those points on our graph. So what we're going to do is we're going to use the intersection on the calculator. So this I'm going to take you through step by step. I know some of you are probably more familiar with using calculators than others, so I want to go step by step with this, make sure we're on the same page with how they use this process. So if you know how to find points of intersection and all, that's really all I'm doing here. So what I'll do is I'll go into my y equals editor, and I'll pop in y1 as my function. y2 and y3 are going to be those boundaries, right? So we've said that our function has to be between 1.8 and 2.2. So I'll graph one of those as y equals 1.8. The other one is y equals 2.2. Doesn't matter which is which. Right? And those are horizontal lines. Remember, y equals a constant? That's a horizontal line. So when I graph those three, right, there's the function, and then the two horizontal lines at 1.8 and 2.2 are very close to each other. Let me change this. All right. So I've got two horizontal lines there, but they're really close to each other. I want to see those points of intersection. So I'm just going to zoom in. Now here's a recommendation. I want to zoom in close to that point of intersection, right, where those lines hit the graph. And now I know specifically the point that I'm interested in. I want to look at that point where x equals 1. So if you want to recenter your graph on a specific point, hit your trace button, and then just type in the number you want to, the x coordinate of the point you want to focus on. So hit trace, and then just type in 1 and hit enter, and that should then locate the point 1, 2, excuse me, on your graph. And what it's going to do is it's going to put your cursor, there's a little X cursor thing on the graph, right? It's going to put it on that point. So then when you go to zoom in, it's going to zoom in specifically on that point that you've indicated. Otherwise, it's going to zoom in right here on the origin. Now also, I've graphed this on the standard viewing window. I did zoom 6 when I graphed it. That's always, I recommend that as a starting point when you're graphing any function. And then you can manipulate your window settings from there. All right. So put those three in, recenter the graph, hit trace, and then enter into your A value so that it centers on that point. And then go to the zoom menu and do zoom in. And I zoomed in a couple times until I could more clearly see those points of intersection. Now you have to be careful here because there are multiple points of intersection, but here's my cursor, which, notice it kind of changed it a little bit. It's no longer at exactly 1, 2, but it's really close. But so it's close to that point that we indicated. But what I'm interested in is finding the points of intersection between now our function and these two lines. But you have to be careful here because there are a couple of different points of intersection, right? I've got one here and I've got one there. We want the ones that are close to our point, right? So we're looking at our graph, right? That's the piece of the graph that we're interested in. We know that this is 2.2. We know that this is 1.8. What are the x coordinates of those points? Right? What's this x coordinate? What's this x coordinate? That's what we're trying to find. That way we can tell you what interval you have to be in to pick those x values. How close to A do I have to be to guarantee that my y values are within this interval between 1.8 and 2.2. Right? So that's what's taking place. All right, now to do that, we're going to find points of intersection. All right, so I want to know what is this point of intersection between our graph f of x, or the curve f of x, and that line y equals 1.8. So to do that, you go to the calc menu, which is second trace. So your second and trace, that's the calc menu that comes up. And then we're picking number 5 for intersect. We want to find the point of intersection between the curve and that horizontal line at 1.8. Now the graph is going to come back up. Notice here it says first curve. Up at the top it's got y1. Hit enter, because you have to tell it what you're doing is you're telling the calculator, well, what do you want to find the intersection of, right? Between what curves or what graphs. So it's always going to come up and say first curve, which is y1. Just hit enter. Now it says second curve, which by default will be y2. And if those are the two that you want to find the point of intersection between, then you're good to go. Now again, notice there are 2 points of intersection. So if that's the case, if there are multiple points of intersection between the graphs that you're using, in this case y1 and y2, just make sure your cursor here is close to the point that you want to find. So in other words, if I was interested in finding this point of intersection for some reason, then I would move that cursor, use your left and right arrow, and I'd move it along that line until it's closer to that point. All right, so whichever point of intersection you're interested in, you want your cursor close to that point. It doesn't have to be exactly on top of it, but it just needs to be closer to that one than the other one. Okay? Then you hit enter, and it'll say guess. I don't care to guess, I want to know what it is. So make sure you hit enter again, and then it will tell you what that point of intersection is. All right. So this was the number that I had on the note, and I used 1.124. Now I'm going to talk a little bit more about that in just a second. So I rounded it to a few decimal places. Okay? And then we're going to repeat the same process to find this point of intersection. Right? Because remember, this is our 1.8, this is our 2.2, and this is our function. I want to know the points of intersection between our function and those two boundary points. So we repeat exactly the same process. We'll go back up here. Go to our intersect. Now when this comes up, right, again, choose intersect, and it'll say first curve. Hit enter. Now when you hit enter, it's going to automatically go to Y2. You need now to go to Y3 because that's our 2.2. I want this one. So hit your up or down arrow and it'll scroll through the Y's. So if I want to go from Y2 to Y3, just hit the down arrow, and now my second curve will be Y3 equals 2.2. And then from there again, it's exactly the same. So once you have, because you have to tell it which ones you want the intersection between. And we have three different curves here that we're dealing with. So then Y3, it'll say guess when I hit enter. Then hit enter again, and you get your point of intersection. And now here, I'm interested in the x coordinates, right? We know what the y coordinate is, it's 2.2. I'm interested in the x coordinates, so 0.91142, etc., etc. Now again, what I did over here, let's get nice. So now I have those points of intersection. I know what the x and y coordinates of those, the x coordinates of those 2 points are. So notice at 0.911, what I did was, looking at the distance between x and a, let me get this back darker, so that distance between x and a. Now on the left side of this thing, the distance from the left side, or the left point that we found, notice that I rounded this up to 0.92. This is what I'm trying to say, and without being too confusing with it. So I started off with this 0.911, and then I rounded it to 0.92. Now on the left, so what we do is we always round up, because I have to guarantee, once all this is said and done, that I have to pick an x value that's within this interval. And on the left side of this thing, it has to be within a distance of 0.911. So I don't want to round that to 0.91, because that's going to put me outside of that interval, right? It's going to drop me to the left of that point. So now I'm outside of the interval that we found. So on the left side, you always round up. So that's 0.9211. I round it to 0.92. If it's 0.919, I round it to 0.92. We always round up, and that, number of decimal places, of course, will just depend on our question. Our directions, or how accurate we care to be. I usually like to go a couple of decimal places if that's the case. Sometimes you see it done more, sometimes less. It's just a matter of how accurate we care to be in a particular question. Now on the right side, notice what I did here was we say round down. That's probably not the best word to use. The proper word would be to say truncate. If this was 1.125, I would still use 1.12. So it's not that we're rounding it, we're truncating it. We're just dropping this number off. I don't care if it's a 9, 1.129, I'm still using 1.12 for the same reason that we said over here. If I round this, if it was 1.125 and I rounded it up to 1.13, I would be outside of my interval, right? I would be over here somewhere. So now be careful that with that part of it. So we say we always round up on the left. Once you find your numbers, round up on the left, and I'm going to say truncate / round down on the right. And it's just to be safe. It's just to make sure that we are within the specified interval. So now I have an interval of values for the x. I know that if x is between 0.92 and 1.12, then I'm going to be between 1.8 and 2.2 on my y-axis. But we need to choose a delta value. We need to choose that distance between x and a that's uniform. I want the same number on both sides, same distance on both sides. So what we'll do is we'll find the distance between x and a on the left, the distance between 1 and 0.92 on the left of 1, our a value, is 0.08. And on the right side, the distance between 1.12 and 1 is 0.2. Right? So I'm a distance of 0.08 on the left. I'm a distance of 0.12 on the right in our interval. But we want that to be uniform. We want the same distance on either side. So for our delta value, what we'll do is we'll choose the smaller of the two. All right? So we choose delta to be the smaller of the two values. So I'm choosing, oh, that got away from me. I choose delta to be 0.08. And so once all of that, everything that's said and done here, what we're finally saying is if I choose delta to be 0.08, then I want to choose x values that are within a distance of 0.08 of our a value, which is 1. Then that would guarantee me that I am within a distance of 0.2 of our limit. And it guarantees me that I would be somewhere at this location on my graph. All right, so that's a specific example. I'll do another one of those, again, just to give you the idea, but that, essentially what you're doing is once you specify the epsilon to be a specific number, then you know what these are. Those then become the y coordinates of the point on your graph, and then you just want to know what are the x coordinates of those points. And to get those, we found the points of intersection between our graph and those two horizontal lines. And then the rounding, as I described, just to make sure that we are within our interval. All right, so here's another example, and this one's a little bit quicker. Now we kind of have the idea. This one taken directly from the homework. It's number 4 on page 113. We're using the graph of f of x equals x squared to find a number delta such that if that distance between x and 1 is less than delta, then the distance between x squared and 1 is less than 1/2. Right? Now, if you want to put this in terms of that limit definition, right, then I'm looking at the limit as x approaches 1 of x squared, which is our function, is 1. Right? So here's our a value, here's our l value, here's our function. So the limit as x approaches 1 of x squared equals 1. That 1/2, there's that distance between x squared and 1, that is your epsilon, right? Because that is the distance between f of x and l. And so like I said, now you graph it. We have the function graphed, x squared. We know what these two lines are within a distance of 1/2 of 1 puts me at 0.5 and 1.5, right, on either side of 1. And then we find those points of intersection just as we did before. All right, so I would graph y1 would be our function, x squared. And then y2 and y3 would be these two guys. Again, doesn't matter which is which, you just keep track of which one when you're finding your points of intersection. So I'm going to go y2 and y3. And then we find those points of intersection as we did before. All right, and on the left, you would find your point of intersection would be 0.707. So again, notice I rounded up automatically to 0.71. On the right, 1.224. I truncated it, 1.22. Again, if that would have been 1.225, I would still use 1.22. So then we've got our distance on the left, the distance between our a value, which is 1. It's always tricky when your a and your l are the same. But this is our a value. The distance between 1 and 0.71 is 0.29. On the right side, the distance between 1 and 1.22 is 0.22. And so as before, we take delta to be the smaller of the two. So choose delta to be 0.22. Then I guarantee you, if you choose a value that is within 0.22 of 1 in this interval, then I guarantee you will be within this interval on your y values. All right. So again, you're guaranteeing that you're going to be in this part of the graph by choosing x values that are within that interval. All right. So those are specific examples where we knew exactly how close we wanted to be. We knew what epsilon was. And then we had to find the specific delta that would make that happen. These next couple of examples, it's going to be more generic. So without specifying the epsilon value, you tell me how close to A do I have to be, what is delta, so that for any epsilon value I give you, you can tell me exactly what the delta value would be. And to do that, we're going to get delta, or we're going to come up with a value for delta in terms of epsilon. So that way, whatever you choose this to be, I can automatically just calculate what I want that to be. All right. Now again, these are probably the more hair-pulling parts, right? Because it's very generic and it's very specific in terms of the steps that you have to follow, but it's a process. Right? And so if you follow the process step by step, they're all done exactly the same way. But I'm going to call these an epsilon delta proof, or you prove using the epsilon delta definition of the limit. So here's our limit statement. We're proving this limit. Remember, that's what I said earlier. Ultimately, that's what this is all about. It's proving that this limit is exactly true. So it doesn't matter what value you choose for epsilon. I can always choose a delta that gets me within a certain distance of my function. So I'm proving this limit as x approaches -2 of 1/2 x plus 3 equals 2. We're proving that that is actually true. We're going to find delta. I always recommend you start with this generic statement, and then you're just going to plug pieces in from there. So we're going to find delta such that the distance between f of x and L is less than epsilon whenever the distance between x and A is less than delta. Right? So I'm guaranteeing that the distance between f of x and L is less than some epsilon value whenever I choose the distance between x and A to be less than some delta value. And I'll be able to tell you what that delta is if you tell me what the epsilon is. So then start with that generic first statement and then just plug everything in. Right? What is f of x? That's our function. So the distance between f of x and L. What is L? Whenever x minus A is less than delta. Right. So the distance between f of x and L is less than epsilon whenever the distance between x and A is less than delta. And then I went ahead on this side, I just went ahead and rewrote that first as the absolute value of x plus 2 is less than delta. Now, here's the trick to these, okay? So I've got the absolute value, and I went ahead and simplified on this left side. Let me get ahead of myself. So I went ahead and rewrote the left side. Plus 3 minus 2 gives me plus 1. So now here's what I've got. I've got 1/2 x absolute value of 1/2 x plus 1 is less than epsilon whenever the absolute value of x plus 2 is less than delta. Here's the trick to these. Since I want to come up with a value for epsilon in terms of delta, then I'm going to turn this into a version of this so that I have the same thing being compared on both sides of this expression. So that over here I have x plus 2 compared to delta. If I can get x plus 2 compared to something over here, then whatever this is has to be the same as that. Or at least it can be replaced as an equivalent. Okay? Let me get all that out. That probably made absolutely no sense, right, or very little sense. But that's the basis of, I didn't want to knock all that out. Let me leave that. Let me back up. I didn't want to wipe that out. Hang on. Okay. All right, I wanted to get rid of, give me with me just a second. Get rid of that. Yeah, so we can go back through this. There we go. All right, so I need to turn that left side where I have the comparison to delta. I want a version or some version of x plus 2, or absolute value of that, so that I can change or compare the epsilon to the delta if I have the same comparison on the left and on the right. Now again, these are all going to follow the same process. So I said it may seem a little bit confusing at first, but I said we'll go through a couple of examples. It may make a little more sense, hopefully. So once I do my f of x minus L is less than epsilon, simplify that, and I need that to look like this. So since I need x and I have 1/2 x, what we're going to do is just we're going to factor out the 1/2. Now be careful of the algebra here. So I'm looking at this statement, this absolute value of 1/2 x plus 1. I want to rewrite that by first factoring out the 1/2, and I guarantee you whenever you pull that coefficient off, you're always going to end up with exactly what you need left. So in other words, if you factor 1/2 out of this, you will end up with x plus 2. If you don't believe me, do redistribute. That would give me 1/2 x plus 1/2 times 2, which is 1. Right? So you factor off this coefficient. That will leave you with the statement that you need here. Now, here's absolute value. Be careful. Absolute value of a product is equal to the product of the absolute values. All right, so there is some basic algebra to be careful of here, and I'll show you, especially in the next example, how if you ignore that, it can lead to some issues, some mistakes. So the absolute value of a product is equal to the product of absolute values. So I went ahead and broke that up. And now I've got the absolute value of 1/2, which is 1/2. So that's how I got from this to this. It's not just a matter of factoring out the 1/2 out of the absolute value. It works that way in this case because that is a positive constant, the 1/2. Again, my next example, I'll be a little trickier with the signs on those things. But now that gives me what I wanted. I said I wanted to turn that into some version of x plus 2, or absolute value of x plus 2. I have that. And now if I solve that inequality for absolute value of x plus 2, I can tell you then that the absolute value of x plus 2 would have to be less than 2 epsilon. Now I've got x plus 2 compared to something here, and I've got x plus 2 compared to something there. So if absolute value of x plus 2 is less than 2 epsilon, and absolute value of x plus 2 is less than delta, then we are going to choose delta to simply be 2 epsilon. And if I choose delta to be 2 epsilon, then that absolute value of x plus 2 would be less than 2 epsilon. And I simply replaced this with this. But what we're ultimately after, I said the whole objective here is this. That's what we're after. We want to know, what does delta have to be to guarantee that I'm within epsilon of our limit. Okay? Now, there's a second part to this. I'm mostly interested in what we've just done, but there is a second part to this. We'll actually show or prove that it works. So if you choose delta to be 2 epsilon, does the statement still hold true? So we're going to show that it works. So that we're just going to take things in reverse. Right? Remember, our original statement said that the distance between f of x and L is less than epsilon whenever the distance between x and a is less than delta. So let's reverse that. And let's say now, okay, in the opposite direction. If the distance between x and a is less than delta, right, so there's the distance between x and -2, which then gives me x plus 2 is less than delta, then the distance between f of x and L, which would be this. Now notice you actually end up doing exactly the same thing you did to find delta. So I start off with, if the distance between x and a is less than delta, then the distance between f of x and L, and then I just simplify it again, and then I factored out that 1/2, would be less than 1/2 delta. Why? because if x plus 2 is less than delta, then 1/2 times x plus 2 would be less than 1/2 times delta. And then I can replace delta with our 2 epsilon, because we said we're going to choose delta to be 2 epsilon, which leaves me with 1/2 times 2 epsilon, which is epsilon. So ultimately what this statement says is, if that distance, if x plus 2 absolute value is less than delta, then the distance between f of x and L is less than epsilon. Gotta love algebra, right? Because that's all this is. It's an algebra rewriting of that thing. I'm going to do another one. I'll give you another example with that, because I know it is tricky, and the first time you see that, it's like, what? I have no idea what the heck you just did. All right, so let's do another one. Oh, and also I made note, this is our overall limit definition that I gave you, the epsilon delta definition. It also holds true for right-hand and left-hand limits. Now I'm not gonna burden you with those, but page 109, page 112 also gives a similar definition for the one-sided limits, right, the right-hand, left-hand limits. It also gives you a similar definition for infinite limits, but I'm not going to bother with those. So you can kind of reference those, but it's very much the same type of definition. Right, but that's just for completeness sake. All right, so here's another example. Let's see if we can make a little more sense of this one. So we're looking to prove the statement using the epsilon delta definition of a limit, that the limit as x approaches 10 of 3 minus 4/5 x is -5. All right. So again, we start with our generic statement. What do we want? We want to say that the distance between f of x and L is less than epsilon whenever the distance between x and a is less than delta. So if you start with that statement every time and then you just plug your pieces in, that at least gives you a good place to start. So plug in f of x. What is f of x? That's our function. Minus L. What is L? That's the value of our limit, which is -5. Is less than epsilon whenever x minus a, which is 10 in this case, is less than delta. Okay? And then come over here and work with this epsilon statement. So I've got 3 minus 4/5 x minus -5 is less than epsilon, which then gives me 3 minus 4/5 x plus 5 is less than epsilon. And then remember, our objective is we want to turn that into this. I eventually on this left side need some version of x minus 10. Okay? So it's all about simplification at this point. Take the f of x minus L and just simplify it as far as you can. And I've got the absolute value of -4/5 x plus 8 is less than epsilon. Okay? And then we say we need to turn that into x minus 10. And the first and obvious thing to do is to factor out this coefficient. Right? Because I need x minus 10, let's get rid of the -4/5. And again, I guarantee you this works every single time. If you factor -4/5 out of this statement, and of course that leaves you with x, it also will leave you with -10. Right? You factor out the negative, so that'll change the sign. If you redistribute -4/5 back into that, you will get -4/5 x, and then -4/5 times -10 would give me a +8. Okay? But again, I guarantee you it's going to work every time. Now, be careful here. And again, I kind of left out one of the statements. Absolute value of a product is equal to the product of the absolute values. All right, so I would maybe insert that between those two, because I have absolute value of a product here is equal to the product of the absolute values. And then there's an absolute value of -4/5, which is 4/5. All right. It's always going to end up being a positive value, because remember our initial definition, we said that epsilon was greater than 0. We said that delta was greater than 0. Epsilon and delta will always be positive. That's by definition, because they're distances. Epsilon, the distance between f of x and L. Delta is the distance between x and a. So they're always going to be positive. So then once I factor out that coefficient off of the x, then I'm just going to solve for x minus 10. And now I've got the absolute value of x minus 10 being less than 5/4 epsilon. X minus 10 is less than delta. X minus 10 is less than 4/5 epsilon. So I choose delta to be 5/4, I think I said 4/5, 5/4 epsilon. And there's our value for delta. And that's what we're after. This is ultimately what we are interested in. I want to choose or find a value for delta in terms of epsilon. Now again, the second little part to it is to show that it works. So if you choose delta to be 5/4 epsilon, then do I end up with the difference between f of x and L being less than epsilon? Okay, because that's the initial limit statement. So here's the back end, the second part of it. And again, we go backwards, essentially. We go in reverse. So we'll say if the distance between x and 10 is less than delta, then the distance between f of x and L, which is this, which is that, which is that, and again, that's essentially exactly what we did previously. All of this is exactly the same thing that we did above. Okay. So then that, now, since that is equal to 4/5 times absolute value of x minus 10, since we said right here x minus 10, let me switch to the other, x minus 10 is less than delta, then 4/5 times x minus 10 would be less than 4/5 delta. And then we'll plug in our delta, which we said is 5/4 epsilon. And I've got 4/5 times 5/4 epsilon, which is epsilon. And you should always end up with epsilon there. So ultimately, like I said, this second part of this is saying that if the absolute value of x minus 10 is less than delta, then the distance between f of x and L is less than epsilon. Yeah. So it's tricky. I know it is, and you may, you'll have to digest that a little bit and look at a couple of those. I'm sure when we do our review, we'll have to look at one. But I'm gonna give you one of these on your test, I guarantee you. So it'll be very similar. But like I said, the steps are the same regardless. You follow the same basic steps for any of these epsilon delta proofs. Okay. All right, that's it for that section. That's 2.4. It's a tricky section, so be careful.